Testing, testing, 1, 2, 3. Hope the mic is on. This is on psychometric functions. Sibel is here. Sarah is here.
It was the
Hey, Meg. Hi, Jess.
I have some stuff on my phone. I have my phone out, or I might have to.
Okay, thanks for letting me know.
Just so you know.
Yeah, thanks.
yeah. I know. Very good idea.
Hello, Zach.
No regret. There's this guy that I worked with. He was like obsessed with me. It was like, he thought I was the weirdest guy in the world, and he wanted to marry me. I was like, this is go away. Yeah, I was like, well, he worked in the same restaurant that I did, and we like didn't know each other. And we like tried to talk. I was like, this is like, I don't know, like, oh, no. You are yourself.
This is only a test.
When it was on Saturday night, yeah, I walked in for like 5 minutes, and then I went directly to the back, like back to the bathroom. Yeah. And I was like, yeah, I was in the bathroom. Because I've been painting, but like, I was here to be here. Yeah. Oh, they're fun to be so yeah. Yeah. I was actually having no, behind the bar. That's fine. And then right by the bathroom, that's like all the things I not do anywhere else. I was taking my hair straight to the hair, literally for nothing. So.
Okay, we've got 12:30. Why don't we get started? Good afternoon, S&P. Wow, that's a great response for the beginning of week 2. This is the first full week, number 2. And I want to congratulate you all on your TED Ed responses. We had a really good TED Ed response, and we had a lot of folks doing Draw 2 really quite well. So thank you all for that. I'm excited about making that connection with you. Some of you may have received feedback. If you've checked, I'm told, I can't see it from my end, but when I'm working in TED Ed responding to your responses, I find that, students have told me that you get an email. Is that correct? Have people received an email? This would have just come out this morning, so you might want to check at some point. You don't have to check right now if you have a device on you, but you should see some feedback from me, and well done. I'm glad to have all of that. Okay, so what I thought I'd do is just begin with a reminder of what's coming up. Today we're going to be talking about some just noticeable differences, at least in about 10 or 20 minutes. We'll get there. We'll have that conversation today, and then we'll set you up for Wednesday. Wednesday we have another TED Ed, okay, and this is going to be on time estimation. Really fun idea about how time estimation depends on a lot of things, and we're going to see that it depends, for example, on whether we're listening to music or not. We're going to see that time flies when we're listening to music. We're also going to see that it depends on our state of sobriety, and we have one example where we have some rats who are on THC, that's the active ingredient in marijuana, and we're going to get the rats making some estimates about time while they're stoned. So, so we're going to see time estimation of a stoned rat, and we'll be using some psychometric functions and just noticeable differences in time to make those measurements. So I think it's a really interesting conversation. For Friday, we'll do something totally different. For the first time this semester, we'll put the chairs in a big U, and I'll walk in and I will say go, and you will talk about anything you'd like to talk about regarding S&P. I'll try to remain quiet that whole time. I encourage you, if you're so inclined, to find a sensation and perception-related video that you might like to crank up here and show to the class. If you do find one, please try to keep it to under 2 minutes, right? Because if each of you did a 5-minute video, some of you wouldn't get to show your video. You don't have to have a video. You can just say that this is something from the readings that I found interesting, or something from a video that we've done a TED Ed on that you found interesting. Maybe you have a family member who has a special condition for sensation and perception. Maybe you have a visually impaired or auditorily impaired family member and you want to share that. Or maybe you have a pet that has those impairments. Any of that is going to be fine. So anything that you'd like to talk about, it's going to be up to you to keep the conversation going. And we'll encourage you to try to maintain eye contact with each other. Okay, so you won't be looking at me and sort of raising your hand to tell me something. You'll be talking with each other. And we'll see if we can keep the conversation going for 50 minutes, okay, without me talking. We'll see how that works, okay? All right, I'll give you another reminder about that on Wednesday. Okay, any questions about that? Yes, please.
Could it be just about anything, or like it has to be something we've talked about already in class?
It can be anything that's S&P related, and so if you have something that's sensation and perception related that we haven't talked about in class, that would actually be very welcome. It would be some new information. It can be on any of the senses. It can be for any animal. It can be robotic sensation and perception. Okay, that's fine too. Okay, so lots to do. We finished on Friday talking about signal detection theory. So I'd like to warm up. I always like to go 2 steps forward, 1 step back, just to make sure that we see how these topics are all connected to each other. And we started the semester by talking about consciousness, and then we said we needed to figure out how to measure consciousness. And that brought us to signal detection theory. So can somebody remind us, as best you can, what is signal detection theory and why do perceptual psychologists like it? Just in general, what is signal detection theory? And what does it do for us? Okay, thanks, Alexa.
It allows you to look at the actual abilities of a person in terms of perception, regardless of their bias.
Okay, right. So it allows us to get a measure of somebody's perceptual sensitivity. We sometimes call it sensory sensitivity, independent of their bias. Can you say just a little bit about what we might mean by bias?
Like we were talking about, like the liberal versus conservative response bias.
Okay.
And so, basically, whether a person is more inclined to say, "Yes, I noticed that," when they're not sure.
Okay, all right, right. So it could be that two people have identical physiological responses to a stimulus, but it's kind of on the border of detection, and people might have different kinds of response biases. And signal detection theory allows us to actually quantify those. So with that in mind, can somebody remind us what D prime and beta are within the context of signal detection theory? We use beta lots of different ways, even within psychology, but D prime and beta, what do those correspond to? Meg's got something.
D prime kind
sort of tells us the overall sensitivity
Okay.
without bias.
Okay.
And then the criterion data tells us if there's a response bias.
Okay, right, so we're going to use beta as some kind of quantitative index of our response bias, and we'll use D prime to tell us just how sensitive we are. And Zach also had a hand up. Anything you want to add to that, or was that about what you were going to say? That was it? Okay. All right, so let's just throw a couple of quantities out. This is how we were beginning to wrap up on Friday. We started to run out of time. We were talking about some of the quantities. Can you all show me by gesture? I'll keep my hands behind my back. Can you show me by gesture approximately what D prime equals 1 would look like? For those two distributions that we always draw, can you put your hands into the position for, say, D prime equals 1? It's a bit of an approximation. Okay, I'm looking around the room, and I hope you'll look around the room too. It's okay to get a clue from your neighbors. Okay, can you bring it to D prime equals 0? Okay, then back out to D prime equals 1. Okay, D prime equals 3. Okay, and then back to D prime equals 0. Back to D prime equals 3. Okay, that's all looking good. Can somebody tell me what D prime equals 3 would imply? What would it mean? Okay, Alex has something.
The larger the D prime, the easier it is to distinguish between the two symbols.
Okay, right, so the larger the D prime, and that was actually the right gesture, the larger the D prime is what you did, the easier it is to distinguish the two stimuli. And it might be one stimulus from a different stimulus. It might be one stimulus from some kind of background noise, that noise-only distribution, okay, which would be typically on your left-hand side. Okay, what would D prime equals 0 imply? Yeah, thanks.
But the person can't tell that there's something else going on, or they can't detect the other sort of.
Okay, they really can't detect it. It would be 0 sensitivity. We can even think of D prime as a direct indicator of sensitivity. And if you're at 0, you have no sensitivity. Here's one. I don't remember if I did it in this video or another video. So just something that's fun to think about. We certainly didn't talk about this on Friday, so it's a new question. What would it mean to have a D prime equal to, say, -1 or -3? So here's 0, here's 1, 2, and 3. Here's 0, here's 1, 2, and 3. My hands are backwards now, right? This is, if we call that 3, then we call this 0, call this -1, -2, -3. Any ideas about that? Might not be entirely obvious. Negative sensitivity. Any notions about that? Yeah, Tony's got something. Okay, you can kind of think of it as making it harder, although if you're at 0, it's probably pretty hard. You can't tell that there's some stimulation over that background fan, okay? What this means, if we start going toward negative numbers, it basically means that your participant has reversed his or her responses. And what I mean by that is, let's say I'm asking you to say that the tone is present or absent, okay? If you're just guessing, and you really can't tell, you're going to be at D prime equals 0, okay? Suppose we'll take one case where we've actually got a wise guy on our hands. The wise guy hears it very clearly, and says, nah, didn't hear anything, okay? Then the wise guy hears absolutely nothing and says, oh yeah, there it is, okay, right? Now what's going to happen is this thing is going to start moving, this force distribution is going to start moving to your left-hand side toward the negative side. So we might call this the area, the negative area, the area of the contrary observer. This is a contrarian, right? When they hear it, they say, nope, I didn't hear it. And when they don't hear it, they say, oh, yeah, wow, that was really loud. Okay? And you might say, well, why would anybody do that? Well, every once in a while, we'll get somebody from Psych 100 who wants to figure out what happens if I deliberately reverse my responses. Okay? This is different from somebody who doesn't actually hear the distinction we're asking them to make. They don't see the distinction. If they can't see it or hear it, they're going to knock D prime equals 0. If they can see it or hear it, they're going to be reversing the responses, and they're going to generate potentially as big a response, a bigger difference as would somebody at D prime equals 3, but now they've reversed the responses, and we can tell that they're systematically different from 0. And Meg had a question.
What was it called?
The area of the contrary observer. This person's a contrarian, okay? When I say high, I mean low. When I say low, I mean high. When I say absent, I mean present. When I say present, I mean absent. Okay. Another thing that happens every once in a while, sometimes this will happen with an animal or with a human to whom the question is not clear. Sometimes you just give them 2 buttons to press. This one's for present, this one's for absent, right? And they get that mixed up. Okay? Maybe they're not clearly labeled, and they press. They're trying to help. They're not trying to be a wise guy. They reverse their responses. So it appears to be that they're making contrarian responses. Okay. All right, what I'd like to do now is have you take a minute, look over your notes, if you would, and perhaps you can see if there's some questions that you have from signal detection theory on anything related to signal detection theory that I might be able to clarify for you. I always like to prompt you first with TED Ed questions and then to do a little summary, but maybe there's something we just didn't get to that was really not clear. And this is now a free-for-all. Anything that you'd like, I'll try to answer on signal detection theory. And after this, we'll make our way over to thresholds. So take a moment. If you think that's pretty clear and you don't really have any questions, then that's great. I'd like you to think about something else now. Can you think about some creative applications of signal detection theory? In the video, I give you 1 or 2 examples of how sensory psychologists might use signal detection theory for detecting a tone, detecting a light, saying maybe that 2 kinds of stimuli are same or different from each other. You know, it could be that we give you Coke and then Coke, that's same, Pepsi and then Pepsi, that's same, but we can give you Pepsi and Coke and then you'd have to say different, right? That would be a taste discrimination kind of thing. But I wonder if you can think of some really creative ways of applying signal detection theory. It doesn't just have to be in S&P. It can be in any branch of psychology. It can be in any branch of really any field. Signal detection theory really helps us with decision making. You have to make a binary decision, and that can be any kind of binary decision. It happened to be developed originally by sensory psychologists, but it can be used in political science, it can be used in computers, it can be used in economics, it can be used in college admissions, it can be used anywhere. Right? It's really a way of thinking about decision making and teasing out the sensitivity of a system, which could be a sensory system, but it could be a political system, it could be an admissions system. Right? And that system will have some sensitivity, and it will also perhaps have some kind of a bias. Okay? Just like a sensory system would. Okay, yeah, Madison has something.
You could use the example of the legal system.
Okay.
Where if you have enough evidence to support whether the defendant is guilty or not.
Okay, right. Okay, so just like Libby, if we go back to Libby for a moment, Libby doesn't need very much sensory evidence. If she gets just a little bit, she'll say, yeah, I see that, right? You can imagine that there could be juries around the country that act in a relatively liberal way. Again, we're using liberal here in a signal detection way, not in a political orientation way. So with just a little bit of evidence, they might say, yes, that person is guilty, right? Because we do have a default in our country, which is not guilty, right? Okay, and then it's the burden of the prosecutor to make their case. And it might be that the relatively liberal members of a jury would say, well, just that little bit of evidence, yeah, that's probably enough for me. A more conservative juror would demand more evidence. Okay, so that was a very nice parallel. Something else? Just as a heads up, this kind of thing might be like a good test question, right? Where you've already got signal detection theory down, and now if you're a good liberal arts student, you should be able to make connections, right? And we want people to see connections across their courses, connections across their co-curricular lives, and their social lives and their academic lives, okay? So we actually we're making decisions all the time, and most of our decision making can be recast as a signal detection theory problem. It just so happened to be historically developed by psychologists. It didn't have to be psychologists, and psychologists who were S&P people, sensation and perception people, but it wouldn't have to be that. Okay. Anybody else have a creative example? Okay, yeah, thanks.
Any type of sensor or alarm would go off after reaching a certain value, but it's also, they also have to detect like whether or not a false alarm is more important to stay away from the
Excellent, okay. So any kind of a sensor, right, any kind of a sensor, and we have physiological sensors, and there's a fair biological component in this class, but there could be detectors around your house. Maybe you have burglar detectors or something like that. And Zach is making the good point that that system will have some level of sensitivity, and you could set it to be relatively inclined to say yes, I'm gonna put off the buzzer, and I think we've got a burglar, or a little bit more on the conservative side. Okay? Same thing is true for spam detection. Has anybody heard of that inside of your email browsers, right? That we have people in IT, information technology, who are always tweaking, how much of a chance should we take on a given email message? Should we classify it as spam, or do we not classify it as spam, right? And we can figure out, a particular message really was a good message, another one really was spam, and we could measure a given system's D prime and beta. Okay? There's another hand, I think. Does somebody else have one more idea? Connie's got one.
It was more of a question.
Okay.
What did you say about all questions? Like, what kind of questions are sensation perception questions?
So do you mean for the test, or did you mean more generally, like sensation and perception? Okay, so a sensation and perception question would really be about our senses, as one example, okay? That is to say, when we are having our sense of taste or touch or smell or hearing stimulated, okay? That's clearly an S&P question, okay? But you can be somebody who's into politics or into governance, and you might want to know, gee, is it the case that in different regions of the country we have relatively liberal or relatively conservative jurors? If you were to compare the jury system in Ohio to that of California, just to pick two states, you could describe both types of juries by using D prime and beta. And maybe one is more sensitive than the other, maybe one is more liberal or conservative than the other. Okay? But that wouldn't be an S&P question, but it would still be a signal detection answer, right? Because you're using the signal detection framework. Anybody else? With another example, we've had a couple of good examples. I don't want to cut anybody off. Okay, so I think we get that. Why don't we begin to transition into what you did for today? You had a bunch of TED Ed questions, and these TED Ed questions were now on an alternate kind of measurement system. We are scientists, we measure things. We're going to be measuring sensations and perceptions. And we've talked about signal detection theory. Now we'll talk about psychometric functions and thresholds. And just to set a historical tone on this, I think you might get a kick out of this. I'm going to go find me on Google. Here I am. There I go. And somewhere down here at the bottom of my page, Nestor's academic family tree. And I apologize if I've shown some of this. I don't think we did this on the first day. I sometimes do this on the first day. But anyway, we have 3 columns here. And I'm all the way at the bottom of this tree. The way this is, this is me down here. And this is me as an undergraduate. So when I was an undergraduate, I studied with a guy named Robert Allen. He did his PhD with a guy named James Matthews, who's not related to me. It's a coincidence that we happen to have the same last name. He studied with Russ Church, Rich Solomon, Holzberg, Holt, William James. Anybody recognize that name? Okay. So I am in William James' intellectual lineage. And because you are my students, you too are in William James' intellectual lineage. Okay. Who's following that? Okay. And then who did he study with? Hermann von Helmholtz. Who's heard of that person? Okay, you probably heard about that in Psych 100. If you're taking, or if you've taken history and systems, those names will certainly come up. In fact, many of these names will come up. Let's see. And then I have him studying with Mueller and Rodolphi, and at some point the trail runs cold. We don't know historically what happened. At some point in our history, we weren't issuing PhDs or MDs, right? Back in medieval times or prior to that, they didn't really have doctorates. But as far as I could trace my intellectual history, that's where they are. And that's me as an undergraduate. I studied at Fairleigh Dickinson, and I graduated in 1993. My point about just noticeable differences is I also got a PhD from Brown. I studied with Leslie Welch, Suzanne McKee, Gerald Westheimer, Glenn Fry, by the way, who got his PhD at OSU, William McDougall, Mueller, Lotz, Fechner. How many people remember that name? Gustav Fechner. Okay, or Weber. Weber's who he studied with. Okay, we're going to be studying just noticeable differences in the PowerPoint that you had for today, and those were first measured by these two. Okay? In fact, they sometimes refer to the Weber-Fechner law for just noticeable differences. Right? How many people remember hearing something like that, just noticeable differences? Okay. So then we're going to be using the psychometric functions. We're going to try to figure out how big a difference in whatever, how big a difference in tone or in saltiness or in touch pressure, how big a difference do you need to detect it? And these were initially measured by these folks. And you can see that you go straight on down the line. My doctoral lineage brings me right back there. It's not too surprising that the people way back when who were measuring thresholds have academic offspring like me and now like you, who are interested in measuring thresholds. Okay? Then I did a postdoc, and here's my postdoctoral line, but that's another story. I just thought I'd connect you to Weber and Fechner, some folks from the history of psychology, who are very interested in trying to figure out how do we measure these thresholds. Okay? So let me go there now. Okay, this was the psychometric functions. Okay? And we had some TED Ed questions on this. Okay, so the first one that we had was something like this. In your own words, briefly describe the branch of psychology known as psychophysics. Anybody want to help us out with that? Okay, Jess has something. Okay, right, the physical and the mental. So as psychologists, we can think of psychology as the science of behaviors, thoughts, and feelings. And we typically are going to be measuring behaviors, thoughts, and feelings. And that's typically going to wind up on our y-axis. Okay? And then psychologists are also experimentalists in many cases. We're going to be manipulating something, an independent variable, on our x-axis. And in this class, we frequently will be manipulating physical properties of stimuli. We might manipulate the intensity of a sound, or the intensity of a light, or the frequency of a light or a sound. So we've got physics on this side, and we've got psycho on this side. Okay? So our handshake is psychophysics. That's our gesture. Can we all do that together? Psychophysics. Say it with me. Psychophysics. And again, psychophysics. We're psychologists. We measure psychological phenomena. Okay, that's going to be our dependent variable. And we're going to have some kind of manipulation. In this class, because we're interested in sensations and what's driving our sensations, we're going to be manipulating the physical stimulation. And what's intriguing there is that we're going to just have a little bit of introduction to physics throughout this semester, but very often we can draw some inference about the biology that's intervening there. Right? We have some physiological structure that's picking up this physical energy and converting it into some kind of a response for us. Okay? So we're going to be thinking about psychophysics, partly so we can learn about psychology, partly so we can learn about the biology that's allowing us to interact with the physical stimulation in our environment, psychophysics. Okay? Okay, and to do that, we're going to use some psychometric functions, which is a type of a function. Can somebody help us out with what a mathematical function is? Okay, thanks.
A rule for turning one number into another number.
A rule for turning one number into another number. That's all that is. Okay? And you can draw it out as an equation, but you can also just draw it out as a graph. So there are graphical representations of functions, and there are numeric representations of functions. They're actually the same thing, two different ways of looking at the same thing. Okay? Can somebody remind us what the linear function is? From 7th grade, you probably learned a very famous equation. Go ahead, Meg's laughing. Who remembers that little ditty? Y equals mx plus b. Okay, that's a function. It's a very simple function, but it actually does a lot of work for all of the sciences, including psychology. We frequently have a simple linear function. Sometimes, though, we find out that the data that we're interested in have nonlinearities. That is, they're not well described by a simple function. But even a simple linear function is a rule for turning one number into another number. We stick in an x value, we get out a y value. That'll be true here. We're going to stick in an x value that might correspond to our physical stimulus. So a function is a rule for turning one number into another number. They have numbers, they have pictures. Okay. All right, so question 3 was, why might the x-axis, or the abscissa of a psychometric function, reflect relative rather than absolute stimulus values? Anybody want to help us out with that? Relative rather than absolute stimulus values? A couple of hands. Meg's got something. Okay.
I didn't know if this is correct, but I thought it was because of the standard that was chosen.
Okay.
Because in different situations they would be like the professional baseball versus just like a little league. Like the standard would be different for like a 90 mile per hour versus like it's not an absolute because it doesn't stay the same between like little league doesn't have a 90 mile per hour standard.
Right.
So it changes, so it's relative rather than.
Excellent, excellent. So in that Meg's response, she invoked the standard. Typically, we're going to have some kind of standard stimulus, and then we'll present other kinds of stimuli that are going to be more intense or less intense than that standard. And of course, you can make that standard anything that you want. You need to make it relevant somehow to the question that you're asking, relevant to your participant, which might be a human, might be a non-human, might be a system, might be a computer system of some variety. Okay, but you need to have some kind of a standard, and then give it stimulation. Absolute threshold and say, ask the question about how sensitive is the system to detecting anything. Okay, but assuming that the system can make a detection, can it now begin to discriminate or classify? This was slower, this was faster, this one was hotter, this one was colder. Okay. Can somebody tell us about the relationship between a psychometric function slope and sensory thresholds? So Meg reminded us that we have these linear functions, and they have a slope and they have a y-intercept. Okay. A psychometric function has a slope also. Okay. So how does this go? Relationship between the slope and sensory threshold. Claire's got something.
Aren't they the inverse of each other, or don't they have an opposite relationship?
Okay, so can you tell us about that?
So if you've got a high slope and you have a low threshold.
Okay.
Or vice versa, if you have a low slope, you have a high threshold. So like if you had a high threshold for pain, you would have a low feeling for, or like you have a low threshold.
Yeah, no, that's she said the same thing a couple of different ways, and she was correct each time. Right, so there's an inverse relationship between these two. We might call that a negative relationship between these two. So we can plot some psychometric functions, and we can see how steep they are. Almost like asking the question that Meg was alluding to with our linear equation. We can say y equals mx plus b. In that equation, which letter or variable corresponds to the slope? Y equals mx plus b. M, okay, right, so the bigger the m is, the steeper that slope is going to be, the further away it is from zero, okay, in either direction. Okay? Claire is pointing out that we can have really, really steep psychometric functions, okay? And if we do, that's going to typically mean that we have low thresholds, and it's a little bit hard to hear when the person is speaking in the front of the room, so I'll just repeat what she said. If you have really low thresholds, you have high sensitivity. Okay? So those two are inversely related. You might remember that from Intro to Psych, and you might not remember that from Intro to Psych. How many people did have that in Intro to Psych? The threshold and sensitivity are inversely related. It might depend on what you're remembering. It might depend on who you had. And what they mentioned when they were doing sensation and perception in Intro to Psych. Okay? So now we have a couple of ways of talking about sensitivity. Right? What we can do is we can talk about D prime, right? And we can also talk about things like thresholds, which would be evidenced by very, very steep psychometric functions. Okay. Let's see what else we have here. I do want to spend some time actually tracking some psychometric functions. I think it'll be fun. In fact, why don't we'll take one more question on this, and then we'll actually do a demo or two where we track some psychometric functions. Okay? So I wonder if somebody can help us out with contrasting ceiling effects and floor effects in psychological studies, and what those might look like in psychometric functions. But sometimes you'll hear about ceiling effects and floor effects. When a psychologist talks about that, what does that mean? Bobby's got something.
A ceiling effect is when you get to a certain point, and beyond that point, it doesn't have any more effect on the other effects. So like pain medication, you only go so high in pain medication before it stops.
Okay, right. Okay, so for pain medication, maybe a little bit helps me a little bit more helps me a little bit more, a little bit more helps me still more, but at some point we kind of top out. We call that an asymptote. We've reached something of a ceiling. You can continue to change the x-axis, but you've maxed out on your y-axis. You're not going to be going any further. Okay? That's the ceiling. We've hit the highest point that we can measure on our dependent variable. Okay? Might be obvious now what the floor effect is, but can somebody just unpack it for us? Might be helpful to think about a floor effect. I'm thinking about maybe a task that you have to perform, and some tasks are relatively easy, some tasks are relatively difficult. Anybody want to put that into context for us? Easy versus difficult tasks, ceiling effects versus floor effects. How might that come together? So a lot of us find calculus to be relatively challenging. Okay? Say we gave a calculus test to a bunch of first graders. How are we going to do? People are laughing. How would you have done? I can tell you I would not have done well as a first grader. I didn't do so well in high school. I did okay. But high school was tough enough for me in calculus, but kind of got through it. I don't think I could have done that in first grade. Okay, so we give a bunch of calculus questions to a first grader. Is that a floor effect or a ceiling effect? Floor effect, because their performance is going to be on the floor. They're going to be near 0% correct. Okay? How about if we give a bunch of simple one-digit addition questions or one-digit subtraction questions to 12th graders? How are they going to do? They're going to be on the ceiling, right? So And we're going to try to construct a psychometric function. And we're going to try to construct something that looks like this, as you saw in the video. Okay? And hopefully I'll come to some values that aren't too flat. Okay? This would be the floor effect. This would be the ceiling effect. I'll try to find something in green. I do the same demo with different classrooms. I do something like it in intro. I've done it with different kinds of audiences. And sometimes we wind up a little bit on the red side here. This might be a little bit too easy. But why don't we see how we do? Okay? So here's the game. I'm going to go out to the internet. And I'm going to go to the online tone generator. And I'm also going to try to call up this. We'll do pitch memory. And I think, okay. All right, and what I'm going to do is I'm going to play a tone that's going to be near 440 hertz, 440 cycles per second. So as this tone comes out of the speaker on that projector, okay, it's creating little vibrations in the air that are hitting your eardrum. And 440 hertz means that the vibrations are actually hitting your eardrum 440 times per second. We might have some musicians in the room. Does anybody recognize this as a particular... Okay, what do you know about that?
It's A. It's the note that it is, and that's what like strings will like tune to.
Okay.
Before like concerts and stuff, usually they tune to 440 hertz.
Okay, really good. Okay, so how many people think they might be able to find, if I had a piano keyboard right here, you could find middle C? How many people think they could come up and put their finger on middle C? Not everybody's familiar with that, but some of us know where middle C is. If you went to the note that is the A above middle C, and if the piano were tuned correctly, it would be 440. Here it goes. Can you tell me, is that loud enough? Do you need to be a little bit louder? Okay, that's 440, and I'll play that a couple times. Then what I'll do is, just to give you some example, I'll play a note that's way higher than that. Whoa. Excuse me. The num lock needs to be on. 8. Okay, we all agree that's quite a bit higher. I can take it down by an octave and put in 220. Okay, so those are basically ceiling effects. You could easily tell that those were different from each other. But what I could do, and I will ask you in a moment, is to turn your chairs around, okay? And we're going to ask you to report sharper or flatter. A sharper tone, for some of us are musicians and we know what that means. That means that we're going to be higher than some standard. Meg was pointing out a moment ago that we're going to pick a standard. Our standard is going to be 440. I'm going to randomly jump around on this frequency space, and I'm going to put in some notes that are higher, and I'm going to put in some notes that are lower. And what I'd like you to do is keep your eyes closed so you can't see anybody else responding. And I'll ask you to raise your right hand on trials when you think the tone that I'm playing is higher than 440. A musician would call that sharper. Half of the tones will be higher or sharper. The other half of the tones randomly interleaved are going to be lower. Okay? So you can think of this as the right and left sides of a psychometric function. And we'll see if we can get a group level threshold, a group level JND through our psychometric functions. So you can take a moment, spin your chairs around, move the furnace off a little bit. Shouldn't feel bad about that. Okay, And one other thing I need to do, can you all please put your right hand way up and hold it way up? And it needs to be, okay, I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. One more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, hands down. Thank you. I've got an N of 17. And what I'll do is I'll try to capture what proportion of students are responding. And so I'll ask you to keep your eyes closed, okay? And remember, if you think it's sharper, please raise your hand and keep it up nice and high so I can make my count. And then I'll turn the tone off, and we'll go on to the next trial, okay? So just as a refresher, I'll go back, and here's the standard tone. This is 440, okay? The question will be, from here on out, is it sharper or flatter? Raise your hand if you think it's sharper or higher. So here we go. Eyes closed, first tone. Okay, you can keep your hands up if you had them up. Okay, and if they were down, leave them down. Okay. Okay, thank you. You can put your hands down, and I'm going to record the frequency of your response. Takes me just a moment to get there. Okay. And let me try a different tone now. I'll play it. Here we go. Okay, now raise your hand if you think it's higher, but keep it down if you think it's lower. Okay, so one. Okay, thank you. Hands down. I'm going to record that response. It does take me just a second to pop back and forth between Excel, where I'm recording the response, and the others. Okay. Let me do another one. Here comes, here we go. Okay? And the question is sharper or flatter? If you think it's sharper, hands up, please, and we'll keep them up. And if you think it's flatter, hands down. Okay, and keep your hands up so I can count. Okay, thank you. Going to record that. Okay, I'm going off to another one. Here comes. Okay. If you think that's sharper, raise your hand. If you think it's flatter or lower, keep it down. Okay, I'll stop the tone. Please keep your hands in the air. If you have them in the air, leave them down. If you have them down, thank you. I've got that counted. I'm going to record that. Okay. Let me go to another one. Here we go. And keep your hands up if you had them up, and down if you had them down. So 1, 2, 3, 4, 5. Thank you. Put your hands down to rest for a moment while I record that. Okay, let's go to one other one. Here we go. Here's the tone. Okay, keep your hand up if you think it was sharper. Thank you. I've got that. I'll record it. Okay, we'll go to one other one now. Just a few more. We're most of the way there. Okay, here comes the tone. Okay, and keep your hand up so I can count, or down, so just whatever you decided is fine. 1, 2, 3. Thank you. Okay. Okay, here comes the next one. This is the third to last one. Okay, I want people vote with their hands as they like. Okay, thank you. I've got that. I'll capture that number. Okay. Second to last one. Here it comes. And I'll let you vote as you like. I'm going to make my count. Okay, thank you. Hands down. Okay, and this will be our last one. Oops. Okay, here we go. And we'll ask you to keep your hands up if it's already up. Okay, that's it. Okay, thanks very much. You can spin around. Okay, now, because I didn't have a lot of time to come in here and find the best fitting function, let me just show you what we have going on for the moment. These are your responses, okay? And I was having the sharp ones over on this side and the flat ones over on this side, and it's the proportion of sharper responses that we're getting. Your data are shown here in this dark blue or black kind of a color. If we had absolutely perfect responses, all of these data points would be pinned all the way down, and if we were perfect over on this side, we'd be pinned all the way to the ceiling. Okay? So when it's physically sharper, remember, so well physics, it's physically sharper, you'd be saying sharper 100% of the time. When it's physically flatter, it will lower. similar along to what we learned about in the point of subjective equality. Okay? And here's this beautifully measured psychometric function that's very, very neutral. Okay? We have somebody like Libby who's quite liberal with the, that was a sharper response, and she's going to be giving us lots and lots of those. Okay? And then Connie's going to be more conservative with that response. Our rule is always this: we start at the 50-yard line, we march over, we drop down, and we find the physical stimulus that corresponds to that person's point of neutrality. Right? So here they're even Steven. They're just as likely to say sharper as they are flatter. For this person in red, that might be happening at like -3. Okay? For the person in blue, we have to go all the way over, wrap around, that might be happening at +3. And for the person in green, that might be approximately 0. Okay, so we can have a relatively liberal responder, a relatively conservative responder, or somebody who's neutral. Okay? It's kind of like the Goldilocks and the 3 bears. Okay? Right? And that's too liberal, that's too conservative, that's just right. They all have very similar slopes, though, you might notice. Okay? So their sensitivities are the same, but their biases are changing. Who's following that? Okay? When I come back on Wednesday, it'd be fun if we could have one more. We'll have you spin around, and we'll have you now try to engage in some kind of spatial localization. I'll tap either here, or I'll tap over on this side, and we'll have you make left-right judgments of some standard center, right? And we can see how fine you are on auditory localization. Same kind of a layout. Okay? That's what we'll have when we come in on Wednesday. Okay? Keep an eye out for the TED-Ed questions that are already available. We'll be talking too about time estimation, and we'll use some psychometric functions to talk about time estimation while we're on music and while we're on pot. Okay? Okay, I look forward to seeing you Wednesday. I'll see a few of you in just a few minutes. Have a great day.